Okay, so we're next going to talk about a somewhat pesky or helpful phenomena, depending on your perspective. So it's called Anchimeric assistance, otherwise known as neighboring group participation. So nucleophilic substituents such as halogens, carboxylic acids, alcohols, and amides can react via intramolecular SN2 reactions. As we've previously established, intramolecular reactions are generally quite fast, as the nucleophile and electrophilic carbon are held in close proximity. Now, to help you visualize the stereochemical outcome of these intramolecular reactions, so quite simply in this case, our nucleophile is our internal alcohol, and it's attacking from the opposite face to our iodine. So if our iodine is in the back, the alcohol is attacking from the front. So another way to help visualize this structure is to think about it from a chair-like perspective. So in this case, if we rotate and we twist our molecule into a chair-like conformation, we can see that if we wanted to form a six-membered ring and attack the opposite face of our iodine, our methyl group would be pointing down. So let's make a model and let's help visualize a little bit of what's going on here. So allow me one moment, and during this time, I'd like you to as well put together your own model of this straight chain molecule, as it can help you visualize this idea of intramolecular SN2 reactions. Sorry, one moment. Okay, so here is our model of our straight chain molecule. We have our alcohol and we have our iodine. Is our iodine pointing towards us or away from us? So looking at our perspective, is the iodine pointing towards or away from us? Towards us. Matches the wedge depiction shown. Perfect. So now our alcohol is going to attack behind the iodine. So our alcohol, oops, let me show this from this perspective. So here is our iodine. Here's the back of the iodine, and our alcohol is going to attack from the back. So in another perspective, if I'm holding the back of the iodine to the camera, the alcohol is going to reach around and it's going to attack the back of the iodine. Now, from this perspective shown, is the alcohol pointing towards or away from us? Is the alcohol pointing towards or away from us? Towards. Okay. So let's attack and let's invert our center. And that in turn gives us the following. Here we go. That in turn gives us the following molecule. So as we can see, our alcohol is pointing towards us. And is this methyl group pointing towards or away from us? Is this methyl group pointing towards or away from us? How is this methyl group? It's pointing away from us. The alcohol is pointing towards us, and the methyl group is pointing away from us. And that's why the methyl group gets the characteristic dash. So another way to visualize this approach, since there are many ways, is we can try looking at our molecule in a chair-like conformation. So we can try looking at our molecule in a chair-like conformation. Okay, so here is a sample. Okay, so here is a sample chair, whoops, one moment. So here is a sample chair-like depiction of our molecule. Now, looking at it from the side-on perspective, so looking at it from the side-on perspective for our key bond-forming event, our alcohol is going to attack the back of our electrophilic carbon, and it's going to displace our iodine. Okay, so that's what's going to happen in this process. So we're going to displace our iodine. Our center is going to undergo an inversion. Okay, and now what we do is now that we have our desired carbon-oxygen bond formed, we take a look at our structure, and then we ask ourselves the question, if we look at our methyl group as drawn, and we're looking at this molecule from the side-on perspective for the chair conformation, let's show this one more time just to help everyone visualize what's going on here. Let's show this one more time just to help everyone visualize what's going on here for our key bond forming event. So first we start off with our normal straight chain. So we start off with our normal straight chain, and the iodine, oops, one moment. Let me get the perspective exactly like that we see in the drawing, just so that way we're consistent. Okay, so here's our starting point once again. The iodine is pointing towards us. Now we're going to make a chair-like conformation. So we're going to rotate our molecule. Okay, and now to show you again the key bond forming event, we are attacking the back of our carbon iodine bond, and we're forming our cyclic product. Okay, so after displacement, here we go. We have the following cyclic system. Now my question to all of you is this methyl group axial or equatorial? Is this methyl group axial or equatorial? Axial. And is this methyl group pointing up or down? Is it axial up or axial down? It's down. Exactly. So this structure is equivalent to the following structure. So these two are identical. So you can either think about it from the perspective of drawing SN2 reactions like you did for linear systems, or you can make a chair-like conformation and just form your nucleophile bond to the electrophilic carbon and then draw out the resulting chair conformation. Either way works. And in fact, you can look at both chair conformations, and there are many chair-like transition states you can draw for this process. So here, our internal alcohol is attacking the backside of our carbon iodine bond. We generate the following chair conformation, which is equivalent to the following structure. Now you may be saying, wait a second, aren't these two structures different? Well, they're just two different views of the same structure. Allow me to demonstrate. So currently, so from this view, from this face-up view, our methyl group, let me just adjust this really quickly. Okay. So to match, okay. Get the camera just right here. Okay. So from this view, the methyl group is on the right and it's pointing up. Wonderful. Now, if we just rotate our molecule 180 degrees, now our methyl group ends up on the left and is pointing down. So these two structures are identical, except they're just rotated 180 degrees. And both are acceptable answers for drawing the product of this intramolecular reaction. Does this idea make sense in terms of how to draw and predict the products for these intramolecular SN2 reactions? It follows exactly the same rule as normal SN2 reactions, except you can also draw chair-like transition states and use axial or equatorial designations. Okay, so we've established that intramolecular reactions are pretty fast and they're generally quite favorable. So just to make sure we're comfortable predicting the products from intramolecular reactions, I'd like you to predict the product of the following reaction shown here. So take a moment and predict the product or products of this reaction and try to draw it out using the annotate tool. I'll give everyone about 3 to 4 minutes to work through this problem, and then we'll discuss as a group. I'm just checking that the model kit looks proper. Oh, whoops, I have it flipped. And don't be shy to draw your proposed solution using the annotate tool. Yes, there is. Iodine, it functions as a leaving group. And the amine's the nucleophile. And don't be shy to message me your questions in the chat. And if not, we'll discuss in about 2 to 3 minutes. And I'd like to see at least 1 to 2 responses using the annotate tool, using either the chair confirmation method or just the normal SN2 reaction prediction method to designate the products of this reaction. And don't worry, any response will serve as a valid tool for the remainder of our discussion. Would anyone like to volunteer? Just we'll spend about a minute more and then we'll discuss, but I'd like to see a few responses from students. And just as a reminder, the SN2 reaction occurs with inversion of stereochemistry at the stereocenter. Would anyone else like to propose a solution before we discuss as a group? Okay, so let's discuss. So first and foremost, SN2 reactions occur with inversion. So if our hydrogen is pointing towards us and the iodine's pointing away from us, when the nitrogen attacks, we'll be attacking from the front face with inversion of our stereocenter. So just to show what that looks like, here is our reactant. Everyone notice how the iodine is pointing away from us? Does everyone notice how the iodine's pointing away from us? Good, okay. So now our nitrogen is going to attack from the front face opposite to our iodine. Okay, now let's form that desired carbon-nitrogen bond. Okay, so here's our same view once again. And now, is our nitrogen pointing towards or away from us? Towards, yeah. So we'll just draw what we see now. Now, to help make this a little bit easier to compare to our model, I've rotated this structure slightly. So we've decided that our nitrogen is pointing towards us. Okay, perfect. Okay, now let's take a closer look at our stereocenter now. And we clearly see on the carbon attached, we have a methyl group. And what group is pointing away from us on that carbon? So looking at this carbon really closely, we have the nitrogen in the front, and what group is in the back? What group is in the back? Well, if we say that the ethyl is just flat in the plane of the page, what group is going to be in the back? What group is pointing away from us from this perspective? The hydrogen, yeah. So, just to check our work, that this depiction is correct, let's go through and let's assign some priority. So this molecule is equivalent So let's assign some priority here. So looking at our product, this group is priority 1, 2, and 3. So we have an R stereocenter. Okay, perfect. Now let's look at our other stereocenter. Let's go through the chair conformation just one more time. Let's go through the chair conformation just one more time. So that way we can demonstrate the inversion of this stereocenter. Okay, perfect. So here is our molecule. The iodine is pointing away from us. I'm now going to distort this molecule into a chair-like conformation. Okay, so now that we have this molecule in a chair-like conformation, let's view our critical bond-forming event. So we're attacking opposite to the iodine with inversion of our stereocenter. Okay? So we're going to attack opposite to the iodine with inversion. And we're going to look and see whether our substituents are axial or equatorial. Okay. So after the attack, so just drawing out the chair conformation that we observed, so here's the molecule from the side-on view where our nitrogen is taking the place of the carbon pointing up in our chair conformation. And again, we formed a bond with this carbon right here. So in terms of drawing out our chair conformation, the nitrogen displaced our iodine. So just to show before our attack, just looking at our key bond forming event. So before our attack, we had our ethyl group. So if we're looking at this from a chair-like perspective, let me adjust this slightly. Here we go. So from a chair-like perspective, we had our ethyl group behaving as if it was pseudoaxial, while our hydrogen was acting as if it was pseudoequatorial. After the attack, we had an inversion of our stereocenter. And now, looking after our critical bond forming event, my question to all of you is, so looking at this structure, is our ethyl group axial or equatorial? Is our ethyl group axial or equatorial? So looking at this ethyl group right here, it's equatorial. So let's draw that out. Let's just draw that out for what we see. So from our perspective, just to correct our perspective to account for okay, our amine displaced the iodine, and now drawing what we see. Here we have our ethyl group, equatorial. So in terms of our product, so our nitrogen is here, our ethyl group is equatorial, our hydrogen is here. Okay, perfect. So in terms of the bond forming event that took place, again, just to show that one more time for our critical bond forming event. So we attacked opposite to our iodine. From our side-on view, if we look at our hydrogen and if we look at our ethyl group was behaving as if it was pseudoaxial, and our hydrogen was behaving as if it was pseudo-equatorial. We then formed our desired bond with inversion of our stereocenter. Okay? So now we are left, So now we are left with the following molecule, and we've clearly established that our ethyl group is pseudo-equatorial while our hydrogen is axial. Now, is this ethyl group equatorial up or equatorial down? Is this ethyl group equatorial up or equatorial down? Looking at this chair conformation here, is this ethyl group equatorial up or down? Equatorial up. So we can draw this structure like so. Okay, now there are many ways of viewing this structure. So if we wanted to view this structure from the perspective, that we've initially drawn. So let's look at this molecule from a top-on view. Let's rotate it now. Okay, whoops, one more flip, and there we go. So we've now rotated it so it's drawn in a similar fashion to that which we see in this first depiction. So looking at this structure after we've gone through it piece by piece. Now, if we tilt this structure, so looking at this structure from a top-on view, this structure is equivalent, if we rotate it 180 degrees, to the following, where we have our hydrogen pointing up and our ethyl group pointing down. Perfect. So in terms of other ways of viewing this structure, we can also tilt this structure like so and view it from the perspective where the ethyl group is like a flat chain. And in this case, so looking at the following view, which is the one that we've originally drawn, is the nitrogen pointing out of the page or into the page? Is it pointing towards or away from us? Is the nitrogen pointing towards or away from us? Pointing towards us. And is the hydrogen pointing towards or away from us? Away. Perfect. So depending on the perspective that you're using to view your molecule, you'll draw it in a slightly different fashion. So these would be the two ways of drawing your product from this reaction, respecting the stereochemistry involved. Okay, so let's keep going now. Now to tie things together, Anchimeric assistance, otherwise known as neighboring group participation, occurs when you have nucleophilic substituents present in your molecule and you try to run a typical SN2 reaction. Now, one note, the two substituents inside your molecule must be trans and have the correct geometry for SN to attack. When this happens, you observe a competing intramolecular reaction. In this case, our alcohol is attacking and displacing the chloride in an intramolecular reaction. Now, of the two conformations, only one of the conformations is actually reactive in this process. If we have a trans diaxial arrangement, an intramolecular displacement can occur. Now, once we have this cyclic intermediate, in this case an epoxide, the resulting cyclic intermediate can then react in subsequent SN2 reactions with external nucleophiles. Now, the problem with Anchimeric assistance is, if we look at this reaction in detail, if we look at this reaction, just think about what's going on here. If this is an SN2 reaction, what is odd about the stereochemistry of our reactants and products? Has there been a retention or inversion of stereochemistry in this reaction? Yeah, there's a net retention of stereochemistry. Or in a more proper sense, there was a quote-unquote double inversion of stereochemistry. There was one SN2 reaction, so this is SN2 number 1, followed by a second SN2 reaction, which is SN2 number 2. So we've doubly inverted our stereocenter, which results in a net retention of stereochemistry. Does this idea make sense to everyone? So when you have an internal nucleophile, it can participate in an intramolecular SN2 reaction, which results in a net retention of stereochemistry. So Anchimeric assistance is essentially where this one stereocenter containing a nucleophilic group transfers part of its stereochemical information to another stereocenter via this double displacement. Does that make sense to everyone? Does this idea make sense? It's essentially a series of SN2 reactions occurring. One intramolecular, the second intermolecular. Does this make sense so far? This can cause problems in synthesis when you're trying to just perform a normal SN2 reaction and suddenly your adjacent substituents start to influence and perform intramolecular reactions. So, Anchimeric assistance can also be observed for acyclic systems. So if you try to displace this iodide with sodium bromide, first and foremost, this thioether is a competent nucleophile and it engages in an SN2 reaction, displacing your iodine. Next, your bromide then attacks this cyclic intermediate, resulting in a net retention of stereochemistry. In other words, a double inversion. Okay, let's keep going. So I'd like you to take a moment and look at the following structure, and I'd like you to predict the products of the following reaction, and I'd like you to draw a mechanism for the following reaction. We'll take about 4 to 5 minutes to work through this problem, and I'd like to see at least one student draw out a proposed solution using the annotate tool. And we'll discuss in about 3 to 4 minutes. And don't be shy to message your questions via Canvas or via the chat function. And I'd like to see at least one person break out the annotate tool and try to draw a mechanism for this reaction. And we'll discuss in about 3 minutes. Does anyone want to volunteer and try drawing a mechanism or at least drawing the structure for your predicted product? This is a classic Anchimeric assistance SN2 reaction. If not, we'll discuss in about 1 minute. Would anyone like to try drawing out or proposing a reaction mechanism for this reaction? No worries, it's okay. Let's discuss this together as a group. So first and foremost, in terms of our mechanism, so acetate is a nucleophilic group that can participate and engage in Anchimeric assistance. So first things first, our acetate will attack and displace the chloride, generating the following cyclic intermediate. Okay, once this cyclic intermediate is formed, then our nucleophile, which is iodide, will then attack our least hindered carbon. And is that going to be the tertiary or secondary carbon? Is that going to be the tertiary or secondary carbon? The least hindered? Let's get some responses from the class. Which carbon will be attacked preferentially, the tertiary or the secondary? If this is an SN2 reaction, we'll attack the secondary carbon and displace our internal leaving group. And that in turn will give us the following product. It almost looks like we had a complete retention of stereochemistry in this case, which is indeed true. So in effect, what has occurred is we have a double displacement. Which results in a net retention of stereochemistry. So always be on the lookout for potential intramolecular nucleophiles that can participate in Anchimeric assistance. Does this idea make sense to everyone so far? Does this idea make sense, the idea of Anchimeric assistance? Okay, perfect. So let's keep going now. We're next going to talk about a second class of substitution reaction known as the SN1 reaction, named after substitution, nucleophilic, and unimolecular. So this is seen quite readily when we look at tertiary alkyl halides, where mechanistically, the mechanism involves departure of the leaving group prior to nucleophilic addition. So an SN1 reaction occurs in two distinct steps. It's a stepwise reaction. Now, a few things that are interesting to note, if we look at reaction of tertiary alkyl halides with alcohols, we see that our methyl and primary react the slowest, while the secondary and tertiary react faster, with the tertiary having the fastest rate of reaction. Let's try to explain why that is. What's the mechanistic basis for why tertiary substrates react faster via the SN1 reaction? Well, in the SN1 mechanism, first and foremost, our leaving group leaves to generate a carbocation. Okay? This step is our rate limiting step. In other words, the slowest step. After our leaving group leaves to generate our carbocation, next our nucleophile attacks the carbocation. Okay, so it's a stepwise process, with the slowest step being the generation of your carbocation. So to showcase this reaction, let's look at a tertiary substrate and let's draw a mechanism for the following SN1 reaction. So first and foremost, let's draw out our alkyl halide. So in our first step, first and foremost, our leaving group is going to leave. We draw this with equilibrium arrows because this first step is in fact reversible. Okay, now that we have generated our carbocation, our nucleophile is going to add to our carbocation, and in turn, we're going to generate our addition product. Finally, as the last step a solvent molecule, such as an equivalent of solvent that I'm going to write just as a B, just a basic, well, or relatively basic atom in our solvent, is going to abstract our hydrogen to generate our neutral product. Most SN1 reactions are run under neutral to slightly to heavily acidic conditions. Now, one thing to note about the SN1 reaction produces a mixture of stereoisomers. So it's not a stereo-specific reaction. It produces a mixture of stereoisomers. Does this mechanism make sense to everyone so far? Any questions so far? Okay, let's keep going then. Let's look at an SN1 energy diagram. So it's a stepwise reaction. And our first step is rate limiting. So carbocation formation is rate limiting. We can see this clearly by the fact it has the highest activation energy. We generate a stable carbocation intermediate, and we know that step 1 is step 1 exergonic or endergonic. If we want to start to understand this reaction, is the first step exergonic or endergonic? Are we going up in energy or down in energy? It's endergonic. So the first step is endergonic. So we're going to start to look at the relative energy of our carbocation intermediates to assess the relative energy of our transition states. So the rate determining step is slow formation of the carbocation. Once you make your carbocation, it reacts pretty quickly. So the rate law for an SN1 reaction only depends on substrate. So it's substrate dependent. Only. The rate of an SN1 reaction doesn't depend on the nucleophile. The second step is relatively fast. So step 2 is fast and non-rate determining, non-rate limiting. So what this means, if you compare an SN1 and an SN2 reaction, is that an SN1 reaction, in general, SN1 reactions, do not depend on the nucleophile. You can use a strong nucleophile or even a very weak nucleophile. It doesn't affect the rate of the SN1 reaction substantially. Okay. So just to highlight this again, this is a first order reaction that's only dependent on the concentration of the alkyl halide, and it's independent of the nucleophile. So it doesn't necessarily matter what nucleophile you use. A carbocation is just so reactive that the rate of reaction is relatively fast. So much so that it's not rate limiting. In terms of the stereochemistry of the SN1 reaction, a carbocation is planar and achiral. So the carbocation can react equally from either side, and the product is racemic in nature. You can either attack from the top or the bottom face of your carbocation, and there's no clear preference. So you often get a mixture, almost 50-50, of stereoisomers. So again, SN1 reactions produce a mixture of stereoisomers. Okay, let's keep going with this idea. So just to really hammer home this idea. In SN1 reactions, you generally produce a racemate. However, you have slight biasing of your SN1 reaction where you observe a slightly larger amount of inversion. Now you may ask, why do we see slightly more inversion? Well, after our leaving group has left, the leaving group and the cation generate what's known as an ion pair, where there's an electrostatic interaction between your anionic leaving group and your cationic carbocation. This blocks one of the faces, which results in a slight bias towards inversion. This is very slight, so it's like 60-40. So you functionally have a racemate. This is what makes SN1 reactions not particularly useful if you want to generate optically pure material, or if you want to preserve the optical activity of your material through multiple steps. SN1 reactions just obliterate your stereochemical information. Does this idea make sense to everyone? This is a critical difference between SN1 and SN2 reactions. In SN2 reactions, you see inversion. In SN1 reactions, you see a mixture of stereoisomers. Does that make sense to everyone? Okay, let's keep going now. So looking at the characteristics of the SN1 reaction, the SN1 reaction proceeds through the rate-limiting formation of the carbocation, right? So as a result, if we think about our first step, which is endergonic, our carbocation energy directly affects the relative energy of our transition state. So then our rate increases as our carbocation stability increases, just like we observed for cationic addition reactions. So, as we can see, the most stable carbocation are our tertiary, secondary, benzylic, and allylic carbocations, while our primary and methyl carbocations are not very stable. This is why, in general, SN1 reactions don't occur for primary substrates. So again, just to reiterate this, methyl and primary electrophiles are not very useful for SN1 reactions unless they're allylic or benzylic. So allylic or benzylic are the only case where you'd see reaction of a primary alkyl halide or other electrophilic carbon in an SN1 reaction. Does that make sense? So again, SN1 reactions are driven, and their rate is driven by relative carbocation stability. The more stable the potential carbocation you can generate, the lower your activation energy and the faster your rate of SN1 reaction. Okay, let's keep going with this. Allylic and benzylic halides, just as a side note, because allylic and benzylic cations are stabilized via delocalization of charge, you can end up, when your nucleophile adds to your carbocation, you can end up with a mixture of regioisomers. So you just want to be careful about that. So if I ask you to predict the products, you do have to necessarily be able to predict that you may see regioisomers if your cation is delocalized via resonance. Now, one thing that complicates matters is that your primary allylic and benzylic can react in the SN2 as well as the SN1 mechanism. By carefully choosing your nucleophile and solvent, you can control whether you observe SN1 or SN2 reactivity. Does this make sense to everyone so far? Any questions so far? Okay, let's keep going then. So in terms of the rate limiting step, the rate limiting step for an SN1 reaction is loss of the leaving group. So the leaving group is relatively important for your SN1 reaction. So good leaving groups are generally weak nucleophiles, or they're weak bases or large atoms that can stabilize electron density. This is just a review from our discussion of leaving groups. Positively charged atoms generally make good leaving groups, ergo SN1 reactions are often run under acidic conditions. So sample good leaving groups are shown here. This is just a sampling of the common leaving groups you'd come across in this class. Now, the beautiful thing about leaving groups is you can actually modulate their reactivity using Bronsted or Lewis acid. So under Bronsted acidic conditions, leaving groups can be activated via protonation, right? If we compare hydroxide versus water, water is a better leaving group. Does that make sense? Does this idea of protonation to activate your leaving group make sense to everyone? So this is why SN1 reactions are often run under acidic conditions to activate our leaving group. Similarly, we can activate our leaving group via coordination of a Lewis acid to a Lewis basic lone pair. So if we treat it with a Lewis acid, such as aluminum chloride, we can generate a complex where we have a very electron deficient or relatively electron deficient oxygen, which in turn can leave more readily. So Lewis acid activation is another way of activating a leaving group. Both carbocation formation and Lewis acid coordination function through a similar principle. Okay, let's keep going. So, oops, there should be another chlorine here. So thinking about nucleophiles in the SN1 reaction, since nucleophilic addition occurs after formation of the carbocation, the reaction rate is not normally affected by the nature or concentration of the nucleophile. Once you have your carbocation, it'll react with almost any nucleophile you throw at it, which is useful. Okay, so a classic example of the utility of SN1 reactions is preparing alkyl halides from alcohols. In this case, if we take a tertiary alcohol and react it with a concentrated halogen acid, we'll generate cleanly the tertiary alkyl halide. This is a classic example of an SN1 reaction. So just to showcase the mechanism for this reaction, so we have our alcohol. First, our alcohol is protonated to activate our alcohol. Then, once our alcohol is activated, we don't see an immediate attack. Our alcohol then leaves to generate our carbocation intermediate. Finally, our halide then attacks our carbocation, and we generate our tertiary alkyl halide. So this is a classic SN1 mechanism involving activation of our leaving group via protonation. Does this make sense so far to everyone? Okay, let's keep going now. We already drew the mechanism. Let's talk a little bit about the role of solvent in the SN1 reaction. So solvent effects in the SN1 reaction are due to stabilization or destabilization of the transition state. So polar solvents facilitate formation of the carbocation intermediate, and protic solvents serve to stabilize the transition state and stabilize the carbocation. Stabilizing the carbocation stabilizes the transition state, and it increases the rate of formation of your carbocation. So in general, increasing solvent polarity or utilizing a protic solvent results in an increase in reaction rate. So for example, as you increase the proportion of water in your solvent mixture, your rate is accelerated substantially because water is a more protic solvent. Has multiple hydrogen bond donors and acceptors. This again is another difference between SN1 and SN2 reactions. SN1 reactions love polar protic solvents. SN2 reactions prefer aprotic solvents. Okay, so if we think about solvent effects, the polar protic solvent stabilizes. So the polar protic solvent has a lower activation energy because protic solvents stabilize the carbocation intermediate and the transition state. That in turn results in a faster rate of reaction. Does this reaction coordinate diagram make sense to everyone? Okay, perfect. So let's compare SN1 versus SN2 reactions. So in terms of the substrate, substrates that can easily stabilize a carbocation prefer SN1 reactions. Now, in terms of the nucleophile, strong nucleophiles favor SN2 reactions, while weak nucleophiles favor SN1 reactions. A key feature of the SN2 reaction is the SN2 reaction rate increases with strong nucleophiles, while SN1 reactions are unaffected by nucleophile strength. In terms of solvents, the major difference is that polar aprotic solvents accelerate the rate of SN2 reactions. Polar protic solvents accelerate the rate of SN1 reactions. Now, in terms of the leaving group, the SN1 reactions care a lot about the leaving group. But in general, a good leaving group accelerates both an SN1 and an SN2 reaction. So in terms of our table, in terms of substrates, your primary substrates are overwhelmingly going to be SN2 reactivity. Your tertiary substrates will overwhelmingly react via SN1. Now, in the middle, do you notice how this box is not colored in? These are your borderline cases. So once you looked at your substrate, then you're going to look at your nucleophile. And you're going to say, if we have a weak nucleophile, then we are going to prefer to react via the SN1 pathway. If we have a strong nucleophile, these substrates may prefer SN2. If we have a polar aprotic solvent, that's another hint that the reaction will favor the SN2 pathway. If we have a polar protic solvent, that pushes you more towards the SN1 pathway. Does this summary table make sense to everyone? This essentially has wrapped up a large portion of our discussion today into a short little table. Does everyone understand these trends in terms of deciding between an SN1 or an SN2? Now, you do still need to know what the reaction diagrams look like, the energy diagrams. And that's why we went through and we drew each of them, because those sometimes do show up on the ACS. But what we're going to do is we're going to use this table now, and we're going to look at some reactions, and we're going to predict the products. And the main trick in each of these questions is to decide whether it's SN1 or SN2. So looking at the following reaction, let's go through it piece by piece. Step one, let's look at our substrate. What is our substrate? Is it primary, secondary, or tertiary? Primary, secondary, or tertiary? Secondary. Oh, so it's a borderline case. Yep. So let's now look at our nucleophile. Let's look at our nucleophile. Is ethane thiol a strong or a weak nucleophile? Ethane thiol, is it strong or weak? It's a strong nucleophile. Another thing I want you to note is this reaction is run under basic conditions. That's another little thing that gives you a hint that you're dealing with an SN2 reaction. Okay, let's look at our solvent now. Let's look at our solvent. Is our solvent protic or aprotic? Protic or aprotic? Aprotic. So looking at each of our factors, we have a strong nucleophile and an aprotic solvent. So what mechanism will this reaction follow? SN1 or SN2? SN2. Again, just looking at our table, secondary substrate, strong nucleophile, polar aprotic solvent, looks like a clean SN2 reaction to me. So then, in terms of drawing our mechanism, we attack from the back of our carbon-chlorine bond, and we invert our stereocenter. Here we go. Because we have an anion in solution. The fact we have a negatively charged species implies that we're at least run under slightly basic conditions. Does that make sense? So anytime you see an anion, that's a key signpost that you're running under basic conditions. And that's why when we draw our product, we draw one product. There's no plus enantiomer. We have one product and one stereochemistry. SN2 reactions occur with inversion and are stereospecific. Whatever you start with, your product has inversion at the stereocenter. Does that make sense? Let's have you now work on another example. Or before we talk about a follow-up, let's now introduce two other types of reactions into the mix. Because you're often not going to look at substitution as SN1 versus SN2. There are two other types of reaction pathways that can take place, and these are known as elimination reactions. So elimination is a competing side reaction for substitution reactions. Now, this could be either an undesired side reaction, or you may want to generate the elimination products. In terms of general rules for products from elimination reactions, Zaitsev's rule states that the more highly substituted alkene product predominates in most cases for elimination reactions. Why? It's the most stable alkene. Remember our discussion of alkenes, that the more substituted your alkene is, the more stable it is? Does that discussion ring a bell to anyone? Does this sound familiar? Perfect, perfect. Now, this is just a rule of thumb. It doesn't apply for all elimination reactions, and we'll see some exceptions in a moment. We're next going to look at a very important reaction known as the E2 reaction. The E2 reaction is a concerted transfer of a proton to a strong base and departure of a leaving group. This is a single-step concerted process. I like to think of the E2 as a relative to the SN2. Both your halide and your base take part in the rate limiting step. So this is our transition state where we are pulling off our proton and our leaving group is leaving. Now, if you notice the way I've been drawing this reaction, the E2 reaction proceeds with an anti-periplanar arrangement of our hydrogen and leaving group. So does everyone notice how the hydrogen and our leaving group are anti to one another? They're on opposite faces of our molecule. This is really important because the E2 reaction is stereospecific. And as a result, we generate one alkene geometry. So depending on the stereochemistry of our starting material, we get an alkene with a defined stereochemistry. So let's just say defined. So just like the SN2, where if we start with one stereochemistry, we end with one product stereochemistry, the exact same idea applies for the E2 reaction. Newman projections are wonderful for E2 reactions because they clearly show, when you look down the Newman projection, they show substituents on both sides of your alkene. So we're going to be using Newman projections and chair conformations a lot when discussing the E2 reaction, both to verify that our hydrogen and leaving group are anti-periplanar and to correctly draw the geometry of our alkene. Don't worry, we'll do some examples of this in a moment. So, just to discuss the kinetics, the E2 reaction follows second order kinetics. The alkyl halide and the base take part in the rate limiting step. Okay, so both our base and our substrate are important. In terms of the energy diagram, this is a concerted single step reaction. Does this remind you of something? Concerted single-step reaction? What chemical reaction did we look at previously that was also concerted and single-step? What does this remind you of? SN2, exactly. Perfect. So, one thing that's interesting about our transition state has alkene-like character. So do you notice in our transition state, we are forming and we're in the process of forming our alkene? Does everyone see how in the transition state we're in the process of forming our alkene? So because the transition state has alkene-like character, and alkenes are stabilized by increasing substitution, the activation energy is lower for the E2 reaction the more substituted your substrate is. So opposite to an SN2, the primary has the highest activation barrier, while the tertiary has the lowest. So the tertiary reacts the fastest. Because the alkene-like transition state is lowest in energy because it's the most substituted. Does that make sense to everyone? Okay, so let's look and see some substrate effects. So the better your leaving group, the faster the rate of E2 reaction, as the carbon leaving group bond is broken in the transition state. Doesn't need too much detail for that. In terms of solvent effects, the rate of E2 reaction increases with base strength. Polar protic solvents stabilize the base, resulting in a lower reactant energy and a slower E2 reaction. Does this look, again, familiar to the SN2 reaction? Yeah, so SN2 and E2 reactions really don't like protic solvents. Well, for one, if you have a protic solvent and you're running something under basic conditions, that's a recipe to get a mess. So E2 reactions dislike protic solvents. They prefer aprotic solvents. Okay, so let's look at the geometry of the elimination. So an anti-periplanar conformation allows orbital overlap and minimizes steric interactions. Now, critically, there has to be an overlap between our sigma bonding MO and our sigma star MO for our leaving group. This orbital overlap is key in order to form our desired pi bond and to break our undesired sigma bond. So just like, for example, remember how the SN2 was a backside attack? You can think about it in the exact same way, where you're dumping electron density into the sigma star and you're forming a pi bond. And the reason why our groups need to be anti to one another is so that way our nucleophilic source of electron density can access your sigma star, can access the back sigma star orbital of our carbon leaving group bond. Does this make sense to everyone? Does this look very familiar to an SN2 reaction? Yeah, it's quite similar in thought. So just like an SN2 reaction is a backside attack, an E2 reaction requires an anti-periplanar geometry because we are donating electron density from our carbon-hydrogen bond, and in turn, we're partially filling our sigma star. That's what's actually causing this carbon-halogen bond to break. So both the SN2 and E2 require specific geometric constraints. Okay, so in terms of predicting products from the E2 reaction, the E2 is stereospecific, and elimination occurs when our beta hydrogen and leaving group are anti-periplanar. So just in terms of terminology here, the first carbon is alpha, second is beta, third is gamma, and fourth is delta, but I forget the Greek symbol for delta. Okay, so the beta carbon is the beta hydrogen is the hydrogen attached to the carbon 1/. So this would be a beta hydrogen. Okay, so the beta hydrogen in our leaving group need to be anti-periplanar. Okay, so we set up and we draw out our Newman projection. So just to show in dash wedge notation, we're looking at meso 1,2-dibromo 1,2-diphenylethane. So the meso compound is completely symmetrical and it looks something like this. Let me make a model to help you visualize this. And I'd encourage you to make a model of meso 1,2-dibromo 1,2-diphenylethane, and then we'll discuss momentarily. I'm just putting together a model because this is best seen as it makes things much more clear. Okay. Okay, so here is our meso compound. Here is our meso compound. So let's show the hydrogens in the back. Here we go. So here is our meso compound. What we're now going to do is we're going to rotate this structure. First and foremost, does everyone see how it's meso? Does everyone see how this molecule is completely symmetrical? How you can split it right down the middle, no problem. Now we're going to rotate this molecule and look down one of our carbon-carbon bonds. And I'm going to rotate it so it exactly matches the depiction shown in this drawing. Okay, here we go. Almost. Here we go. Okay, so we have our hydrogen in the front and our bromine in the back. Does everyone notice how they're anti to one another? Does everyone see how the hydrogen and bromine are anti? Okay, so now what we're going to do is when we eliminate our hydrogen and leaving group, all of our substituents on the left-hand side will be on the left of our alkene. So we're going to draw on our alkene that our hydrogen and bromine are on the left. Does everyone see the hydrogen and bromine on the left? We're going to draw all of the substituents on the right-hand side on the right. So both of our phenyl groups are on the right. And that's it. That's all you have to do to draw the products from this reaction. So as we notice, this product has a defined olefin geometry, and it's an E alkene. Does this make sense to everyone so far? Okay, to test your understanding of the E2 reaction, treatment of, so we're going to now discuss another example. Treatment of RR 1,2-dibromo 1,2-diphenylethane, which is very similar to the example that we observed previously. We end up generating Z1-bromo 1,2-diphenylethylene. So first and foremost, let's generate a model of this structure. Let's generate a model of this structure. Okay, I need to correct. I need to correct the bromine positions. I should have both of the bromines pointing out of the page. So once I make my model, then we can make something interesting happen. Okay, so here are both of our models for this structure. So here's the model of the RR compound. Notice both of the bromines are pointing towards us. Does this look correct? Does this match our drawing? Okay, now what we're going to do is we're going to look down one of our carbon-carbon bonds, and we're going to arrange it so one of our bromines is pointing up, the other opposite hydrogen is anti-periplanar pointing down. Does everyone notice how the bromine and hydrogen are anti to each other? Does everyone see that? They're on different carbons, but they're anti-periplanar. Now, for elimination, we're going to draw what we see. So in terms of everything on the left-hand side, what two substituents we have? We have a hydrogen and a phenyl. What about on the right-hand side? On our first carbon, what do we have? This group is representing what? What is this? What is this representing? What is on the phenyl? Yeah. So we have a phenyl on the left, as well as what else? What's this in the back? The bromine, yep, perfect. Perfect, so we exactly predicted that this is the Z olefin. Here is the Newman projection view just for your reference. Again, we eliminate, these are on the left, substituents on the right are on the right. Now what I want you to do now is to try to draw a Newman projection and E2 product for the SS1 2-dibromo 1,2-diphenyl ethane. So I didn't give you the structure for it, so you're going to have to convert that structure, that name into a structure. Just a hint, the RR structure is given just above. And I'd like to see the starting material, a reasonable Newman projection, and the product from this reaction. So let's take a few minutes. Let's take about 3 to 4 minutes to work through this problem, and then we'll come together as a group to discuss. And don't be shy to break out the annotate tool to propose a solution to this problem. And don't be shy to write out your proposed responses using the annotate tool. and we'll discuss in about 2 to 3 minutes. Any questions so far? Don't be shy to share your proposed solution using the annotate tool. We'll discuss in about 1 minute. Okay, so if we're flipped both of our stereocenters, all we have to do, we don't have to be too clever with this. We just have to draw both of our stereocenters with the exact opposite configuration. So instead of a wedge, we draw a dash. That's it. Okay, so now that we have this in place, let's look at a model of this structure. Whoops, here we go. Okay, so here is the model for this structure. Now, as we notice, both of our bromines are pointing away from us. Does this match our drawing? Does this match our drawing? Yes. Okay, now we're going to tilt our model towards us, and we're going to set it up so our hydrogen and bromine are anti-periplanar. Okay, we've accomplished that. Now, I'd like you to tell me what substituents are on the right. What things are on the right? So so first things first, this is equivalent to a Newman projection where we have a hydrogen pointing up, bromine on the left in the front, a phenyl on the right in the front, a bromine pointing down, a hydrogen on the right, and a phenyl on the left. So then, after elimination, on our alkene, our hydrogen and phenyl will be on the right, and what substituents will be on the left? What will be on the left? The bromine and the phenyl. Exactly right. So our potassium hydroxide is going to deprotonate, we eliminate, and we generate the following products. So we've successfully generated the Z alkene. Perfect. Any questions on this example and drawing Newman projections for E2 reactions? If not, we'll talk about another example. This time, I've given you one stereocenter, and let's try to predict the products of the following reaction. So this is an E2 reaction through and through. and I'd like you, using the Newman projection method, to predict the products for the following reaction. So let's take about 3 to 4 minutes, and then we'll come together as a group to discuss in about 3 to 4 minutes. And just to make this example a little easier, you can assume that the methyl is a wedge, just to make things slightly easier. Okay, so let's discuss this reaction. So here is a model of the following reaction. Does everyone notice how the methyl and the halogen, so the methyl, which is right here on the right, and the halogen, which is a chloride, are both pointing out of the plane of the page. They're pointing towards us. Can everyone see that so far? Okay, now we're going to rotate this structure and we're going to set it up so our halogen and our hydrogen are anti-periplanar. So all we have to do now is draw out our Newman projection and draw what we see. So we have our ethyl on the right, our methyl on the left, our bromine is pointing down in the back. We have a methyl pointing to the right and a hydrogen to the left. Does this match? Does everyone see how the Newman projection maps on from our camera view? Okay, now from here, what we're going to do is we are going to eliminate, so our source of hydroxide will eliminate our hydrogen. And in turn, we generate our alkene. So on the left-hand side of our alkene, what substituents will we have? On our left-hand side, what will we have? So what substituents do we see on the left? So, yep, hydrogen and methyl. Okay, and what substituents do we see on the right? What do we see on the right? What do we see on the right? An ethyl and a methyl. Perfect. So we've in effect generated the Z alkene. Perfect. Any questions on this example? Is everyone getting more comfortable with the idea of drawing and using Newman projections to predict the products from E2 reactions? Okay, let's keep going then. We'll leave this next example for you to work on at home. Now, thinking about stereoselective E2 reactions, so substrates with multiple beta hydrogens can generate a mixture of regio and stereoisomers. So in case one, where we have a mixture of stereoisomers, E2 reactions are selective in general for the E alkene, if there's a choice. Of course, you do get mixtures if there are multiple beta hydrogens. Now, the E alkene is substantially favored, but it's not the sole product if there are multiple beta hydrogens. Now, to look and to see why the E product is favored, if we look at these two structures, and we think about our Gauss interactions, in the top structure, we have an ethyl-methyl and a methyl-bromine Gauss interaction. In the second structure, we have a methyl-bromine Gauss interaction, and our two bulky substituents are separated by an 180-degree angle. So which conformation is lower in energy? Which conformation is lower in energy? The conformation that yields the Z alkene or the E alkene? Which conformation is lower energy? Just using the tools in terms of assessing relative energy of two Newman projection conformations, the conformation required to yield the E alkene is lower in energy. As a result, generation of the E alkene occurs more readily. The second one, yes. This is E, this is Z. Does that make sense? Does the reasoning behind why the E alkene is preferred make sense? Okay, perfect. So let's keep going and let's talk about regioselectivity in E2 reactions. So depending on the choice of base, E2 reactions can give different regioisomers. So if we change from ethoxide to T-butoxide, we get this odd product here. So this is the least substituted alkene. But didn't I just say that in general, the more substituted alkene is favored? Yes, that is true. However, bulky bases result in selectivity for the least substituted alkene. And let's try to explain this looking at our conformations. Now, the approach of the bulky base to generate the most substituted alkene would result in a high energy transition state as the result of steric clash. So, if we try to pull off our hydrogen from our relatively substituted carbon, we introduce steric clash when we have a bulky base. As a result, it's much easier for us to grab a proton and generate the least substituted alkene by deprotonating the least hindered proton. So it's much easier to grab this least hindered proton when you have a bulky base than to reach into the center of your molecule and try to grab a highly substituted and relatively congested hydrogen. Does this idea make sense to everyone? When we try to get the bulky base close to our hydrogen that we need to remove to generate the most stable, the most substituted alkene, we get a bunch of steric interactions that are unfavorable. That's why bulky bases, in general, prefer to remove the least hindered proton and generate the least substituted alkene. Does that make sense? Okay, perfect. So let's keep going. Again, we generate the non-Zaitsev product just because we're mitigating the steric clash between our substrate and the bulky base. So I'd like us to take a moment and look at the following two examples, and let's try to predict the products from each of these reactions. Let's try to predict the product from each of these reactions. So let's spend about 3 to 4 minutes and then we'll come together as a group to discuss. So looking at the arrow pushing, as the E2 reaction is concerted, there's one other set of arrows you need to draw to have a complete mechanism. But otherwise, it looks good so far. Would anyone else like to attempt drawing a mechanism for either of these two examples? Does anyone have any questions in the chat? Mechanistically, you're thinking about the SN1 reaction. As we were dealing with a base, this reaction is the E2 reaction, which is concerted. Yep, so the drawing in blue looks good, except our base is ethoxide instead of T-butoxide. So just get rid of 2 of the carbons. But otherwise, yep, that looks good. And then what's the next step in terms of arrow pushing? Yep. Perfect. And then the leaving group leaves simultaneously. Yep. Perfect. Yep. Exactly right. Perfect. I see a lot of reasonable responses so far. So I'm just going to clear the annotations and I'll draw out the instructor solution. So we have our hydrogen. Ethoxide is not bulky. So we're going to go to make the most stable alkene. So we pull off our proton, we kick out our leaving group, and we generate our most substituted alkene. In contrast, T-butoxide, is it bulky or not bulky? Is it hindered or unhindered? T-butoxide. It's bulky. Okay, as a result, it's going to try to pull the least hindered hydrogen, and in turn, we generate the least substituted alkene. Does this make sense to everyone so far? Okay, perfect. So this is a good stopping point